when we step on a sponge or when we apply load on a soil, the load is going to be taken by the skeleton, if the load application is very slow, or by the pore water because it cannot escape fast enough. And so if this is the case, we're going to have an excess pore pressure that will squeeze out in time, starting from the more pervious boundaries where the water molecules can escape more readily. So once again, if this is the formation and we have a layer that is going to be squeezed, let's say that this is the clay sandwiched between sand and another sand layer. So the initial condition is hydrostatic if this is perfectly saturated. But when we apply the load, this is the initial condition, when we apply the load Q, assuming that the load is applied very fast compared to the clay but not to the sand skeleton will pick up the load, but the clay skeleton can't, and so it will be taken all as excess pressure by water in the clay. And so this is the U excess is equal to the applied load in the extreme case. And so this excess pore pressure is the one that is gradually going to dissipate, and in this with these boundary conditions it will dissipate very fast in both directions, and you're going to see the excess pore fluid pressure. Now if I only plot the excess, U excess, at the beginning, if I normalize by Q, this is going to be 1, and then it's going to escape very easily on the edges and is gradually going to evolve. As you can tell, this appears like a sequence of sinusoids, and so there is a closed form solution, and is the error function, which is a summation of sinusoids multiplied by an exponential. So be aware that there is a closed form solution for very simple boundary conditions, but we would like to solve it numerically for more general cases. So let's start with the simplest form of the consolidation equation, which, remember, is pressure diffusion. In the simplest form is the coefficient of consolidation times the second change in the pore pressure with respect to Z twice. Notice that this is Laplace. This is permeability, Darcy and permeability, steady-state seepage, is equal to the change in pore pressure with respect to time. Now, in order to solve this numerically, probably the easiest way is to do finite differences. And you may recall that the concept of finite differences that starts from understanding that a derivative dy dx is equal by definition to the limit of delta y over delta x as delta x goes to 0. Now, in engineering, we're going to make a simplifying assumption. Well, it's close enough to delta y over delta x if delta x is small enough. The second derivative is the derivatives of the first derivative, and if you go back to the video where we explained this for steady-state seepage, the solution of the Laplace's equation, you are going to confirm that the variation of u with respect to z twice can be replaced by the pore pressure above the point minus twice the pore pressure at the center plus the pore pressure below the point, and this is multiplied times CV. Let me put the delta T here over delta Z squared. And this is going to be, now I need the first derivative, and I already transferred the delta T, but let me say the first derivative of du dt is the pore pressure at the next time minus the pore pressure at the current time. So this is going to be U next minus U center. Now, to explain what I'm actually doing, we're going to discretize this medium, and I'm going to enlarge it. So I am discretizing here the depth, this is Z, into sublayers separated by delta Z. And I'm going to discretize time. So in this direction, I have time in also different time intervals separated by delta T. So this is depth, and this is time, and this is delta Z, this is delta T. So look what this discretized form of the diffusion equation or the consolidation equation is telling us, that the pore pressure at the next point, let's call this the next point, is equal to the pore pressure at the center before, the pore pressure above, the center below. So we have this type of a kernel. This is above, this is the center, and this is the point below. Let's solve now for the U in the next stage is going to be equal to U at the center. I send this to the other side, or I flip things around, and we're going to have, let me replace, let's call beta, this coefficient CV times delta T over delta Z squared. So let's call this beta. And this is the finite difference expression of the diffusion equation. Let's recognize what we are doing. We are defining the pore pressure at the next time interval as a function of the pore pressures in the previous time interval at nodes that are above, at the same elevation, and below. Above, center, and below. And I can compute the next pore pressure. This is quite wonderful because all I need to do is to move the kernel up and down to compute the pore pressures in the next time, and then I move to the next time and I move the kernel up and down and to the next time. There is no need for iteration like we did in solving the Laplace's equation. This is moving along in time. One important caveat, that in order for this to evolve in a stable form, the coefficient beta has to be smaller than 1/2. Which means that once you have a certain soil with a certain C sub B value, coefficient of consolidation, if you choose your delta T, you are automatically going to fix what is your vertical spatial resolution segment. Conversely, if you use small segments, it's going to constrain the times at which you can resolve the diffusion equation. Let's start with a simple example, and let's take this. Assume that we have a condition from the top, so at time t0, we will have values. This is only the clay layer, the one I'm going to capture here, the clay layer. And I don't know how deep it is, but let me show first of all the initial ones. Let's say that this is 10, 15, 20, 25, 30, 35. These are the initials. Then I apply the load, and let's say that the load Q is equal to 50. So immediately after load application, this will go to 60. Now, for the next time step, whatever the next time step is, for your problem with your given delta Z and CV, for the next time step, the pore pressures at the margin are immediately going to dissipate into the sand. So this one will automatically go to 10 and will remain at 10 forever, because that is the hydrostatic condition. The same will happen for the one at the bottom. This will instantaneously migrate or dissipate to fall back to 35 and will remain at 35 because that is the hydrostatic condition. Now the problem is that the values, intermediate values, now we have to begin and apply the kernel. And so let's put the kernel between these values here to compute this value. And we are going to assume for this solution that beta is equal to, let's choose a value, 0.25. So it is the value at above, the value below, which is 60 plus 70 is 130, minus 130 is 0, plus the center, 65. So that didn't change. And if you do the same for all of them, you will see that nothing has changed because we didn't start dissipating. So all these values here will be 70 and 75, 80. And the dissipation has only happened at the edges. Now let's go to the next time interval. And to compute the top values already known from the hydrostatic condition, let's consider this one. So we have to apply the kernel between these elements. And now 70 plus 10 is 80. Minus 130 is 50. Times 0.25 is 12.5 plus minus 12.5 plus 65. This one now will decrease to 52.5. And you see how the dissipation is going to fall off. The same will happen with this element here when I come. This will be 75 plus 35 is 80, 110, minus 160 is twice this value, 160 is going to be 50, another 50, times 0.25 is 12.5 again, minus 80, this will be now what happens with the value? Let's compute one value here, and there are two values that we could that are missing, but if I take this value is 70 plus 80 is 150 minus twice 75 is 150 plus 0 plus 75, 75. So this one didn't change and this one will not change either because the dissipation has not reached that level. Now I move the kernels, I use the kernels to compute the next row, and you will see how the pore pressure will gradually dissipate until you go back to the steady state condition, which is the first line. So this is the hydrostatic condition here. The next solution will give you hints to how to do this for more complex cases. To summarize, the simplest case of the diffusion equation, which we assume that the permeability is constant, that the total load is constant, and it leads us to this simple version of the diffusion equation, can be written in finite differences in this form, where the pore pressure at the next node is computed from the pore pressures at previous nodes. And we show how to do it. You can do it very fast in Excel. This is one column, and then you compute the successive columns instantaneously, very fast. Which means something else. When you have the consolidation data, now you don't need to use magic tricks that we have been maintaining in the geotechnical field to match the experimental data with theoretical solutions to compute the C sub v, the Casagrande solution, for example, in square root of time or in logarithm of time. You can actually try with different CV values and see how this evolves, and you match your experimental results to get the actual CV value without tricks. The simplified diffusion equation makes all these assumptions plus many more, please go back and take a look at the previous video where we derived the equation, because there are so many assumptions that we make. But when they apply, we end up with very elegant solution. Now we go one step before this final solution. There was the situation where we assumed that the applied load Q, this is the applied load, which is Q, was constant. But what happens if the applied load is actually varying with time? That means if in the next time step I put more load, and then the next time step I put more load. And so the solution now we have to bring back the rate of change in the total stress, the boundary condition that we are applying. And so the kernel will not now change, because this is also, when we discretize, remember this part in discrete form, we're going to send the 2 delta t's on the other side, so this will be beta, and this is u above minus 2 u center plus u below, and this one is the u next minus the u at the center minus, and this is sigma next minus sigma at the center. Once again, I already sent the delta t together with delta z squared and sigma v into the beta coefficient. So that means that the u next is going to be equal to u center plus that, plus the change in the total stress, which, if it is increasing, is going to be adding, because instantaneously when you apply that load, the first thing that happens is that the pore fluid pressure takes that load. And so let's write it down in explicit form. This is going to be, let me shift the equal sign. U in the next step is going to be equal to u at the center plus beta u above minus 2 u center plus u below, plus the increment in total stress, which is sigma in the next time step minus sigma in the previous time step. It doesn't have to be at the center. Sigma previous. So this is in the next time, is all a function of values which are, that is next as well, and this is the previous. So let me shorten this. This is next. This is all previous. This is next and previous. As you can see now, the kernel looks the same as before, but we are adding that increment in boundary stress. So if we go back to the previous screen where we had discretized time and space, so this is the value at the next element will be a kernel that once again embodies this one, plus the load increase. So if I plot the applied stress versus time, I may have had 0 stress, then I put so much, then so much, and then a big jump, and then whatever. So the addition is this additional load that now is sigma next minus sigma previous. This is the delta sigma that I am applying in this stress, which is this quantity here, is the delta sigma in this time step. Now, it may be that you want to avoid making these two assumptions of constant permeability and not varying in space or time and constant coefficient of consolidation. If that's the case, you have to go up, further up in the derivation before we made all these assumptions, and explore a more general equation. So we have to create the finite difference formulation for this equation. To avoid confusions, please notice that here is d sigma minus dt minus du dt. Here is the other way around because I reverse the sign by putting the negative sign in the coefficient of CV because the d sigma has a negative derivative. As the effective stress increases, the void ratio decreases. So you can also flip it here, but it will be captured in this equation. So in this case, what is a function of permeability and void ratio? If you go back to video where we talk about permeability versus void ratio, remember that the log, in log scale, permeability, and in log scale of void ratio, these are straight lines. So this is a power equation, and we had many functions for void ratio versus effective stress, which tend to look like exponential decays. However, when we plot it in logarithmic scale, they tend to look more like that. So this is in log of sigma prime, and this is void ratio, but actually the function that we're going to be getting the slope at any given point is this is in linear scale, dE d sigma. And this is the instantaneous void ratio at that depth and at that time. So now it's completely general, and we can use this to understand the self-compaction of very deep sedimentary basins, like, for example, Gulf of Mexico, as the Mississippi River brings additional sedimentary load. And we will need to generalize it in order to get a more accurate examination of the Kansai airport where linear theories, where we keep this constant, does not apply. The Kansai airport near Kyoto in Japan. In summary, consolidation is pressure diffusion, but the actual format of the diffusion equation is only after a large number of assumptions. These are just a few of them. As you may recall, there are many other assumptions that were made. As we begin relaxing some of those assumptions, we have to go higher up in the early stages of the derivation to go to more general equations. And for example, it's very easy to capture the change in the applied load to simulate the loading conditions in real construction operations. Furthermore, if some of the parameters do not remain constant, for example, the volumetric strain with respect to the effective stress or the permeability, then we can go back to even a more general form of the equation. Once again, we put it in finite differences and we resolve it to capture any problem that we have in real field applications.